Did you know that in the time it takes me to say this sentence, the web will have grown by around 5,000 pages? Have you ever wondered how you can send secret messages over the internet when millions of computers can listen in? Join me as I crawl through the internet and start untangling the web. Hello and welcome to Untangling the Web. A quarter of the world's population is already using the internet for email, for downloading music and videos, and of course for the World Wide Web. All this is made possible by some of the most extraordinary results in computer science. For example, later in this lecture we'll see how two people who've never communicated with each other before can exchange secret messages even though all of their communications are public. But how does it all work? Well, to help us find out, Andy has left a secret message for us somewhere on the web. He hasn't said where it is, but he has given me a web address, and apparently if we follow the instructions, we should be able to find the secret message. So let's see what the first instruction is. And he's asking a question. What year was the first Bond film made? Now, adults in the audience will remember what it used to be like when we wanted to find out some information. We'd have to visit a library, and then we'd have to trawl through dozens of books and journals, a process that hasn't changed in centuries. And of course, all of this could, well, take a very long time. And finally, we'd find the information we were looking for. Well, today, of course, is much easier. We simply use a search engine. So let's go to a search engine, and I'll type in first Bond film. And it's brought up some links, so let's go to the first link. And it's telling me that the first Bond film was made in 1962, and it was Dr. No. Now, something very remarkable just happened. The web is huge, and it's growing at an extraordinary rate. If every new web page were represented by a little piece of glitter like this, then this is how fast the web is growing. That's 500 pages a second. Imagine if I'd written my name on one of these pieces of glitter. How long would it take you to find it? And that's just 5,000 pages. There are roughly 15 billion pages on the web. That's 3 pages for every person on the planet. How does a search engine manage to sort through this vast mountain of information and find what we need in a fraction of a second? Well, to find out, we can have a look at this very simplified model of the web. It has just 4 pages, yellow, red, blue, and green. And you'll notice there are links between the pages. So if we click on the word avocados here, for instance, on the yellow page, then it takes us across to the green page. It's these links between the pages which allow us to search the web very efficiently. Now, have you ever wondered how a search engine decides which page to put at the top of the list? Well, it uses lots of different kinds of information, but let's just have a look at 2 of the most useful things. The first of these is called PageRank, and it tells us how important a web page it is, and it makes use of these links. We can see how it works by looking at this water model. So each of these coloured tubes corresponds to one of these web pages, and the pipes between the tubes correspond to the links. So we have a link from the yellow page here to the green page, and over here we have a tube from the yellow page going across to the green page. Now we started out with the same amount of water in each of those tanks. I'm going to go across here and switch on the pumps, and it's going to pump water from one page to another following those links. Now in a moment, when the water levels settle down, the height of the water in each tube will tell us how important that web page is. And already we can begin to see that the yellow page and the red page are not very important pages. The water is quite low. The reason is that these pages just have one incoming link. If you look across at the green page, we'll see that it's much more important. And that's because it has two incoming links. The blue page, however, is also important. Although it has only one incoming link, that link is coming from another page which itself is important. Now, of course, I was making a gurgling noise, not me. On the real web, of course, the computer has to solve this problem for millions of interconnected web pages at the same time. So that's our first example of something which a search engine uses. Our second example also makes use of these links between pages. Let's suppose we're looking for information about avocados. Well, if we click on this green link here, which is on the yellow page, we click on this link that says avocados, it takes us through to the green page. The fact that this says avocados can tell the search engine that the page which it points to is probably about the topic avocados. And we call this anchor text. So search engines combine information such as PageRank and anchor text to decide on which page to put at the top of the list. Okay, let's see if we can get to Andy's secret video then. And we've already found out that the first James Bond film was Dr. No, and that was in 1962. So if we put 1962 into that box, and it says, congratulations, a secure connection has been established. Okay, obviously Andy doesn't want just anybody to be able to view that video. Now I know this is a secure connection because if we look at the web page, we see that the address begins HTTPS. That little S means secure. And also, if we look across here, we see a little yellow padlock symbol, and that again confirms that this is a secure web link. Now, secure links are important if you want to send private information, for example, your name and address or your credit card information across the internet so that nobody else can understand it and copy it. But how are secure links such as this able to keep our information secret? Well, we'll find out after the break. Let's look at how we can send information over the internet but still keep it secret. For this, I'll need two volunteers, please. You are very keen. You come on down. And let's have somebody from this side. Yes, let's have you. You come on down. All right, let's come and stand here. And what's your name?
Josh.
Josh, okay, you wait there. And if you'd like to come and stand here for me, what's your name?
Mark.
Mark, okay, you just stay there. Now, Josh, what I'm going to do is I'm going to send you a secret message, and I want you to unscramble it. But first, to make sure that you don't see what the message is, we're going to pop a blindfold on you and a little pair of headphones. Okay, so here we go.
Is that all right? Just take that.
I'm going to play you some nice music through these headphones, and you won't be able to hear anything that's going on. It'll be just about a minute or so, okay? All right, okay, so he can't hear and see what's happening. So under here, I have my message, so I can now reveal my message. And of course, like everything on the internet and on the web, it's just a sequence of ones and zeros. And we've chosen a nice simple message, 10, 10, 10, just so that you can remember it easily. So the next thing to do is to take this message and to lock it with a key. And again, a key in the electronic world is just a sequence of ones and noughts. But it's very important that this key be generated at random. So to help us do that, we have a special random number generator. Okay, now, what I'd like you to do is just to roll this across the floor nice and quickly and generate lots of random ones and noughts. I'd like everybody to shout out the numbers, okay? Okay, keep going, quickly as you can.
0!
Next.
0!
Keep going.
1!
Right, come on, two more.
0!
One more. 0. Excellent. Okay, thank you very much. You go back to your seat now. Okay, so this is our message, and this is the key. And to lock the message with the key, we have a very simple rule. We take each column at a time, and if the two digits are the same, we put a 0, and if they're different, we're going to put a 1. So these are the same, so they need a 0. These are different, so they need a 1. These are different, they get a 1. These are different, they get a 1. And those are the same, so they get a 0. Okay, so we've taken the message and we've locked it with the key. And we can now send this to our volunteer over here, but first I'm just going to cover up the original message. Okay, there we go. Now we can take off the headphones here. Okay, was that some nice music you had there? Okay, we'll hand those across there. We'll take off the blindfold. Excellent. Okay, now if you'd like to come with me, if you'd like to come and stand over there at that end. So we've sent you a secret message here, which is also called a cipher. And we've also sent you the key that was used to lock the message. So what I want you to do is to use the key to unlock the cipher and work out what the original message was. Now the way we're going to do this is very simple. We take each column at a time, and if these two digits are different, we'll put a 1 in here. And if they're the same, we'll put a 0, okay? So I'll get you started. This first one, these are different, so we put a 1. Okay, can you tell me what goes in there?
That's 0.
That's it, that's a 0, good. And this one?
0, 1.
1, that's it, excellent. I think you're getting a hang of this, good. This is?
0.
0, excellent. This is?
1.
A 1. And finally?
0.
A 0, excellent, okay. So that's unscrambled the message, and just to check, let's go back and reveal the original message. And it is indeed the same. Excellent. Thank you very much. So you've seen one way in which we can lock and unlock data electronically. But there's a huge problem. The sender and the receiver need to have the same key. And it's important that nobody else knows what that key is. And we can't just send the key across the internet because somebody will copy it. Now, for a long time, it was thought that this problem of key exchange was impossible to solve. But of course, without a solution, the whole world of internet shopping and banking and secure websites would never have happened. Let's first look at how we can solve the problem of key exchange in the physical world. And to help me do this, I'd like 3 volunteers, please. Yes, would you like to come on out? Have somebody from there, you can come on out. Let's have somebody from the middle, shall we? Yes, you. That's you? Yep, that's it. So if you'd like to come and stand here, what's your name?
Megan.
Megan. If you'd like to stand there, that's good. What's your name?
Barnaby.
Barnaby. Okay, that's good. And you can stand here. What's your name?
Pippa.
Pippa. Excellent. Okay. So you're going to be our sort of delivery service, okay? And Andy and I are going to try to work out how we can send a key to each other. Now, Andy over there has 2 copies of a blue key. If he can get one of those keys to me, then we can send secret information backwards and forwards. The problem is, the only way he can send things to me is by using our delivery service, and we don't want these people to get hold of the key. All right, so what's he going to do? Well, what Andy can do is he can take one of those keys and he can put it in a box, and he can then lock the box using his red padlock. And once he's done that, he's going to hand it to the delivery service. So if you'd like to pass it down the line, that's good, and send it to me, excellent. And you'll notice, because the box is locked, these delivery people can't get at the key. But the problem is, of course, when I get the box, I can't get at the key either, because I can't open the red padlock. So what I'm going to do is I'm going to take my own padlock, which is green, and I'm going to lock the box using this padlock, and then I'm going to send it back to Andy. Again, the box is safely locked, so the delivery people can't get hold of that blue key inside. And now, when Andy receives the box, it's his red padlock, so he has the red key, so he can remove the red padlock. And once he's done that, he can then send it back to me using the delivery service. And again, the box is still locked, so they can't get inside. Excellent, thank you. And then finally, when I receive it, of course, this is my padlock, and I have the green key to this padlock, so I can remove the padlock, and then inside the box is the blue key. So Andy and I have now managed to exchange keys. We have the same blue key, and nobody else knows what that key is. Okay, thank you very much. Now, this kind of three-way exchange process works very well in the physical world. But in the electronic world, everything is just ones and noughts. And the problem is that the people in the middle would see three messages going backwards and forwards, and it turns out that gives them enough information to unscramble the message and reveal the key. In the electronic world, we're going to need something a bit more sophisticated. What we need is a clever piece of mathematics called a one-way function. We can think of this as something which is very easy to do one way, but very hard to undo. Now, I have an example here of a one-way process. This is a balloon, and it contains a mixture of hydrogen and oxygen. I'm going to set fire to it. Anybody know what's going to happen when I set fire to it? It'll make water. Excellent. What else is going to happen? It'll explode. Okay, there's going to be a loud bang. All right, so I'm going to put on my safety goggles and my gloves. It's one of my favourite bits of the lecture, this. Okay, and I think this is worth a little bit of a countdown. So you want to give me a 3, 2, 1 countdown? Ready? 3, 2, 1. Okay, that was great. Thanks, Andy. So that was an example of a one-way process. It was very easy to take some hydrogen and oxygen and combine them to make water. But to take water and turn it back into hydrogen and oxygen is very hard to do. It needs a lot of energy. So let's see how we can use a one-way process to understand how keys are exchanged on the internet. Now, to help us do this, somebody sitting in the audience, you, I think, is already dressed up, especially for the occasion. So if you'd like to come on down. Would you like to stand there? And what's your name?
Olivia.
Olivia. All right, so Olivia is going to be the internet. And again, Andy and I are going to try to exchange keys, but this time in the electronic world. We're going to send all our information through you, and you're going to try as hard as you can to steal our secret key. All right. So keys in the electronic world are really numbers, but we're going to represent numbers by colours. So each colour represents a different number. And we're going to start with the colour blue. Now, blue is not a secret colour. Everybody knows blue, so I've got some blue, Andy's got some blue, and Olivia's got some blue. Okay. The next thing I'm going to do is I'm going to choose a secret colour, and my secret colour is going to be yellow. Now, I can't just send yellow across the internet to Andy, because it'll be stolen on the way. So to keep it secret, what I'm going to do is I'm going to mix it with the blue. When I mix yellow and blue, I get green. And that's another example of a one-way process. Just took a few seconds to mix the yellow and the blue to make green. But if you had to take the green and separate all the molecules out to get the blue and the yellow again, it would take millions of years. It would be very hard. Okay, so I'm going to take this green, I'm going to send it over the internet. But remember, you're trying to steal all our secrets. So what I want you to do is to make a copy of this colour. Okay, so what I want you to do is to pour half of the liquid into this container. If you just pour it up to that line, that's good. And keep going, a bit more. And I'd stop about there, that's excellent. Okay, and you can pass the rest over to Andy. Now, Andy's going to do something similar. He's going to dream up a secret colour. In his case, the secret colour is red. Again, he can't send the red to me through the internet or it will be copied, so he's going to use this one-way process. He's going to mix it with the blue. So he gets a sort of purpley colour. And now he's going to send that mixture to me over the internet. And again, you're trying to steal our information. You've got the hang of it, so you pour half of it into that container, just up as far as the line. A little bit more, a bit more. Excellent, thank you very much. And you give the rest to me. Okay, so here I have a mixture of red and blue. What I'm going to do is to add my secret colour, which is yellow. So I now have a mixture of red, yellow and blue. Andy's got a mixture of yellow and blue, and he's going to add his secret colour, which is red. So Andy now also has a mixture of red, yellow and blue. So we've managed to agree on the same secret colour. And if we just put these together in the middle, I hope you'll be able to see that those are indeed the same colour. All right, what about our internet thief? What information do you have? Can you make this same colour? Well, let's have a look. Well, this colour is a mixture of red and blue, and that's definitely a bit different. You've got some yellow in here mixed with some blue, so you can't unmix the colours, remember. You can only mix things. So why don't you try adding this to that and see if you can copy our secret colour. And what we'll see is that, that's it, just pour it all in, the whole lot, that's good. Now this is a different colour. It's a different colour because this is a mixture of red plus blue plus yellow plus blue. So it's got twice as much blue in it. And the only other colour you know about is blue. So if you pour that in as well, that's actually just going to make things even worse. There's even too much blue now. You can stop there, that's fine. So we've seen how Andy and I have been able to agree on a secret colour, and in the electronic world that means we've agreed on a secret number. So next time you see that little yellow padlock on your web browser, you'll know that your computer and the website computer have done a little exchange of secret numbers just like this one, and that means it's now okay to put your credit card information or whatever it is into that website because it'll be scrambled and other people won't be able to read it. Okay, thank you very much. Now, the binary keys that are used on the internet are very long, and it would take a supercomputer trillions of years to crack the code by trial and error. But in yesterday's lecture, we learned about something called a quantum computer. This would be able to do colossal numbers of calculations at the same time, and could indeed be used to crack coded messages very quickly. Now, practical quantum computers might be many years away, but what if someone were able to build a quantum computer? Is there a way to send secret messages that even a quantum computer cannot crack? Well, there is, and it also depends on quantum physics. It's called quantum key exchange. I have here a laser, and it's going to fire a beam of light through this, which is a polarizer. The polarizer will filter out all the light except light in a particular direction. Now, this polarizer is vertical. So the light coming through the polarizer will be vibrating up and down in a vertical motion. And we can think of this as somebody sending information. So, for example, they might be in Cambridge. Over here, I have another polarizer and a screen. And we can think of this as the person who's receiving the information. So they might, for instance, be in London. Okay, if we bring the lights down, I'll just turn on the laser. And just going to use a bit of smoke just to help us see the laser. There we go. Now what we see is that the light is passing through the second polarizer and is hitting this screen. What I'm going to do now is to rotate this polarizer until it's at 90 degrees to the first polarizer, and you'll see the light is blocked. So what we've done here is to use this polarizer in London to measure the direction of the other polarizer back in Cambridge. So information has been passed from Cambridge to London. Okay, let's suppose now that somebody wants to copy that information as it goes past. So they're partway between Cambridge and London. Now, with ordinary electronic data, somebody can make a perfect copy of it and we'd never know. But with this quantum key distribution system, something rather special happens. So, let's just take a look at that laser beam. Remember that the beam is being blocked by the second polarizer over in London. And now I'm going to try to measure the direction of that polarizer by inserting another polarizer here. And let's see what happens when I do that. So when I put this polarizer into the beam, we see that light now gets through onto the screen. So this is an extremely peculiar effect. If I remove the polarizer, the light gets blocked again. So inserting this dark material, this dark piece of plastic into the laser beam, actually causes the light to get from here to here. And when I remove this piece of polarizer, it causes the light to be blocked. So if we're here in London, we can detect the fact that somebody has actually tried to copy the information as it goes past. And that means we know that somebody's copied our key and we can't use it safely to send secret information. Okay, I'm going to pop that laser off now. Now, quantum key exchange systems like this are already in use in some banks. And there's even a research group at Bristol that's working on a miniaturized system to go inside a mobile phone. So let's go back to Andy's website and see if we can find that secret information. Well, we've already established our secure connection, and it's now asking me to authenticate myself by typing in the name of my first pet. Well, I've already registered with Andy's website, so I'm going to type in the name of my first pet, which is George, and it says, click here to play the video. So let's click on that link. And while that video is downloading, let's think a little bit about what's going on when we download data over the internet. The internet consists of hundreds of millions of computers connected together in a complex network. And the explosive growth of the internet means that more and more people are downloading more and more information. And just like the roads, the internet can become congested. After the break, we'll find out about some of the very strange effects that can happen when the roads, or indeed the internet, becomes congested. Thank you. Now, you might think that reducing congestion is easy. In the case of cars, you just build more roads. Or in the case of the internet, you just add more bandwidth, for example, more optical fibres connecting cities. But it's not always so simple. And I'm now going to show you something very surprising. Here's an example that looks at the flow of cars along roads between 4 cities. Cars are going to try to get from city A across to city D. Now, this green road is quite a long road. It takes 6 minutes to travel from A to C, and likewise from B to D. The red road is much shorter, but it's quite narrow. The red road becomes congested. So the time it takes to travel along one of the red roads is equal to the number of cars that are using that road. And then finally we have this yellow road, which is a very fast road. It only takes a minute to travel along the yellow road. Okay, let's see what happens if 4 cars try to get from A across to D. Let's see which route they take. Well, the first car wants to go from A to B along this road. That just takes 1 minute. Up the yellow road, which takes a minute, and along the second red road. That takes a minute. So that's 3 minutes in total. What about the next car? Well, the next car wants to follow the same route, but now, of course, this takes 2 minutes for each of those cars because that road is congested. A minute up here and another 2 minutes along there. And likewise with the third and fourth cars, they also prefer to take this same route. So here they are, going along the red road, across the yellow road, and along the second red road. So how long is this taking the drivers? Well, it takes 4 minutes now to go along a red road because there are 4 cars. Remember, this road is congested. It always takes a minute to go along the yellow road, and another 4 minutes along this red road. So that's 4 plus 1 plus 4 is 9 minutes. Now, would any of those drivers like to switch and take a different route? Well, let's have a look. Well, one possibility is to go along here and then this way. That would take 6 minutes plus another 4 minutes, which is 10 minutes. So that's longer, so the drivers don't want to do that. The only other route that a driver could take would be to go up the green road, down the yellow road, and along the other green road, and that would be 6 plus 1 plus 6, which is 13 minutes, which is even longer. So none of the drivers want to go any different route. Now, this yellow road is a very fast road, so obviously it must be helping with the traffic flow. Or is it? I'm now going to show you a very strange effect. It's called Bray's paradox. And to help understand it, I have a physical model of Bray's paradox here. So what we have is a weight that's suspended from some coloured strings from the ceiling. And these are just like the roads. So this red string is an elastic string. That's like the red congested road. And this green string is not elastic. That's like one of the green roads. And then here we have a very short piece of yellow string. That corresponds to the yellow road. And then the second red and green roads are up there at the top. Now you'll notice that these green strings are not under any tension, they're completely slack. And at the bottom there we also have a scale which is telling us how many minutes it takes to travel between those two cities. So at the moment it says 9 minutes. Okay, let's see what would happen if we removed that yellow road. So I have a pair of scissors. And what do you think is going to happen when I cut this yellow cord, which is holding up the weight? Any ideas? What's going to happen? What do you think is going to happen? You think it'll go down more? Okay, let's cut the yellow string and see what happens. Okay, well, very surprisingly, the weight's actually moved up, which means that this journey time has reduced down to about 8 minutes. So that suggests, going back to our roads, that if we remove the yellow road, it might actually improve the traffic flow. Well, let's have a look and see what happens if we remove that yellow road. So let's take these cars off and let's work out which way they're going to go. So now there are only two routes to get from A to D. So the first car, it doesn't matter which way they go. Let's just assume they go along the top here. The second car wants to avoid congestion on this road. So the second car is going to take the bottom route along there and then along there. The third car, again, it's both the same. They could go either way. Let's assume they go along the top there and along that red road. And the fourth car, again, wants to avoid congestion on this road, so they'll take the bottom route. So they go along there and then along there. Now let's have a look at how long it takes these drivers to get from A to D. Well, they each take 6 minutes plus 2 minutes, which is 8 minutes. So that's less time than it took when the yellow road was present. This is a very strange effect, and it arises because these drivers are acting selfishly. They ignore any benefit which their decisions might have for other drivers. And this strange effect can actually happen in real life. In Seoul, in Korea, when they closed one of the 3 tunnels through the city, they actually found that the traffic flow improved. Now, on the internet, the packets of data are like the cars, and the connections between the computers are like the roads. And again, there's no central controller on the internet, which means similar paradoxes to this can arise there as well. So one way to help congestion would be to try to find a way to coordinate the flow of data on the internet. But can we find other ways to reduce congestion? Well, on the roads, one way to reduce congestion is to reduce the number of cars. And we can do that by having more than one person share the same car. I'm going to show you how we can use a similar idea on the internet. So let's imagine we want to download a big file like a movie. Well, we first of all have to break it into manageable sized chunks. And for simplicity, let's imagine that our movie has just 2 chunks, corresponding to the hare and the tortoise. Now, the computer that sends out the movie is called a server. And it could send out these 2 chunks to you, and then to you, and then to you, and so on. But that would take a very long time. And the more people who wanted the movie, the longer it would take. So instead, the server could send the movie chunks to you and send them to you, and then you could pass them on to your friends, and your friends could pass them on to their friends. And that's called peer-to-peer distribution. But now we have a different problem. If you've ever tried to collect sets of cards or sets of coupons, you'll know that it's very easy to get started, but it's really frustrating to get those last few pieces. I'm now going to show you a really clever way to solve this. Now, when you arrived, you all picked a red envelope at random out of a box. I'd like you to open that now. And half of you will find in that envelope the image of the hare, and the other half of you will find the image of the tortoise. So each of you has got half of the movie, and your job is to get the other half. Okay, let's suppose that I'm one of these computers sending out this movie, and let's suppose that I've already got the hare and the tortoise. What piece should I send to you? Well, if I send the hare, then those of you who've already got the hare will get a duplicate, and you still won't have the complete movie. And also, if I sent out the tortoise, those of you who've already got the tortoise would get the same piece twice, and you'll still be missing the other half of the movie. Of course, you could each tell me individually which piece you're missing, and I could just send you that. But that would mean a lot of messages went backwards and forwards. That would take a long time. There's a much cleverer solution, and it's this. I have here a special image that's constructed from the hare image and the tortoise image. What I'm going to do now is to take this image and to overlay it on the images that we have. So there's an image of the hare. When I overlay this image, it becomes an image of a tortoise. And if I take this image and instead I overlay it on the image of the tortoise, what I get is an image of the hare. Now, when you came in, you should also have got another envelope, a green envelope, and if you open that, they're all the same. They all have this special image in them. So if you take your two images and place one on top of the other, and you look up at this white screen here, you should be able to see that same effect. Now, remarkably, we can extend this idea to an infinite variety of chunks, so that there are no two that are ever the same. So if a real movie, for example, had 1,000 chunks, then any 1,000 chunks would give you the original movie, and you'd be guaranteed never to be stuck with duplicates. This means we can avoid sending repeated information, and therefore we can reduce congestion. Okay, let's go and take a look at Andy's video, which should have finished downloading.
You'll never guess what. Chris has got a secret hiding place. He didn't know I was watching, but I saw him hiding something. It's in the cabinet with the light box on it.
Okay, my secret has been revealed. Before I tell you what the surprise is, though, what I'd like to do is just to ask you to imagine a different kind of web. A web in which you could ask your computer any question you like, and it would go and trawl through all the web pages and find out information, analyse them, combine them together, and then answer your question. Now, of course, that would require computers which are much more intelligent. In the final lecture, we look at how scientists are trying to build intelligent machines by allowing them to learn from themselves. Okay, my secret's been revealed, so I suppose I'd better share this with you all tonight. And it is a big bag of sweets. Okay, thank you all very much.